Welcome to the Deep Dive. We're here to break down complex topics and pull out the key insights, just for you, the learner.
Yep, aiming for those aha moments, making tricky stuff understandable without getting lost in the weeds.
And today, we're diving into a really interesting development in AI. It's a type of neural network called pointer networks, PGR nets for short.
That's right. Think of it as teaching AI to solve problems where the answer involves picking things from the input itself, like finding the best route or connecting dots.
Okay, interesting. So it's not just classifying things.
Exactly. It's learning by example how to construct solutions powered by this clever idea of, well, pointing.
Pointing. All right, tell me more. Why is this something you should be paying attention to right now?
Well, think about tasks where the possible answers change all the time, you know?
Like what?
Like maybe sorting photos, the number of photos, the specific photos, they're different each time.
Okay.
Traditional AI models, they often struggle with that. They kind of expect a fixed menu of possible outputs.
Right, a predetermined list.
Exactly. But pointer networks, they offer a way around this. They can literally uh, point to the right elements within the input data itself.
Ah, okay. So the output possibilities can change with the input.
Precisely. And that opens doors for tackling lots of real-world puzzles that were tricky before.
Got it. So for this deep dive, we've gone through the original research paper on pointer networks.
Yeah.
And our mission here is to unpack what they are, how this pointing mechanism actually works, and why they're generating some buzz. All pretty clearly, hopefully without too much jargon.
Sounds like a plan. So maybe let's start with the limitations of the older ways. You mentioned sequence-to-sequence models, neural Turing machines.
Yeah, those are powerful, right. But what's the issue when the output isn't fixed?
Well, their basic setup usually requires knowing all the possible output tokens or categories beforehand, like a fixed vocabulary.
Okay, so it's like trying to order from a restaurant menu where the items suddenly change based on what ingredients the chef found that morning. The printed menu is useless.
That's a great analogy.
Ah.
Yeah. You need a way to dynamically choose from what's actually available now.
So how do pointer networks do that? You mentioned the attention mechanism.
Right. So attention isn't new, exactly. It's a technique networks use to focus on the most relevant parts of the input when doing a task.
Like zeroing in on keywords during translation?
Exactly that. It helps build context.
Yeah.
But PGR nets use attention, well, differently.
How so?
Instead of just using attention to blend input information to help generate an output,
Yeah.
they use the attention scores directly as a point to select an element from the input sequence as the actual output for that step.
Whoa. Okay, so it's not creating something new based on the input. It's literally picking from the input.
That's the core idea. Imagine you're sorting points on a graph. Instead of the AI trying to generate coordinates, it learns to point to the next correct point in the input list.
Like pointing to items on a shopping list in the right order, rather than writing a new list from memory.
You got it. And that's the key advantage. This lets them handle what the paper calls variable size output dictionaries.
Meaning the set of possible outputs can change depending on the length or content of the input.
Precisely. It overcomes that fundamental limitation we talked about with older models needing a fixed output space.
Okay, this pointing idea sounds clever, but, the proof's in the pudding. How do they test if it actually works on difficult problems?
Good question. They really put it through its paces with three quite challenging geometric problems. These are tasks where the output is inherently tied to the input points.
What were they?
First, finding planar convex hulls.
Okay, what's a convex hull?
Imagine you have a scatter of points on a 2D plane. The convex hull is like stretching a rubber band around the outermost points. It's the smallest convex polygon that encloses all of them.
Got it. Like finding the boundary points. Are there normal ways to solve this?
Oh yeah, standard algorithms exist, pretty efficient ones like O(n) log n, complexity.
This is a second problem.
Computing Delaunay triangulation.
Sounds complex.
It's another way to connect those points, but this time with triangles. Following a specific geometric rule, basically, no point should fall inside the circle defined by any triangle's vertices. Again, known algorithms exist.
Right, a specific triangulation structure. And the third, you mentioned the tough one earlier.
Ah, yes, the planar traveling salesman problem, or TSP.
The classic hard problem.
Absolutely. Given a set of cities, find the shortest possible tour that visits each city exactly once and returns to the start. Simple to state, incredibly hard to solve perfectly as the number of cities grows. It's NP hard.
Okay, so convex hulls, Delaunay triangulations, TSP. What's the common thread here for PGR nets?
In all three cases, the desired output, the sequence of points for the hull, the set of triangles. The order of cities in the tour is constructed directly from the input points. You're selecting from the input.
Perfect setup for the pointer idea. So how did they do? Let's start with the convex hull.
They performed remarkably well.
Mm.
Really high accuracy, often finding the exact correct hull. And what was really impressive was the generalization. They trained models on examples with, say, 5 to 50 points.
Uh-huh.
And these same models could then produce pretty accurate hulls for inputs with up to 500 points without retraining.
Wow, that's a significant scale up. The paper mentions something about performance dipping if points were late in the sequence.
Yeah, initially.
Yeah.
But that's where the attention mechanism really shines.
Yeah.
So it looks at the whole input at each step.
Right.
It could effectively learn to go back and pick points that appeared later in the input list if they were actually part of the whole. It wasn't just stuck processing sequentially.
So that dynamic focus is key. Did they compare it against other neural nets?
They did. They compared it to a standard LSTM and an LSTM using attention just for context. The pTRNet was significantly better, especially because the others struggled fundamentally with the variable output length.
Makes sense. Okay, strong start. How about the Delaunay triangulations? More complex structure there.
Yeah, a bit trickier. They achieved reasonable triangle coverage. It showed the network could learn to approximate these complex geometric patterns.
So not perfect, but learning the structure.
Exactly. Part of the challenge was just figuring out how to represent the output, which is a set of triangles, as a sequence the network could generate. They used a specific ordering strategy during training. Getting over 50% correct triangles on sets of 50 points was seen as a pretty solid result.
Okay, learning complex structure.
Yeah.
The big one, TSP. How do PTR nets handle that beast?
This is where it gets really fascinating. They train the networks on optimal, perfect solutions for small TSP instances, like up to 20 cities.
Okay, learning from the best answers for small problems.
Then they tested them on slightly larger ones, like 25 or 30 cities, where finding the perfect answer is much harder. And the pTRNets found reasonably good approximate tours. They generalized.
That's already impressive for an NP hard problem.
But here's the kicker. They also tried training pTRNets on approximate solutions generated by existing heuristic algorithms. Algorithms designed to find good enough answers quickly.
Okay, so learning from pretty good answers, not perfect ones.
Yeah. And in some cases, the pTRNet, after training on these approximate solutions, actually managed to find better tours than the original algorithm it learned from.
Get out. So the student surpassed the master, in a way.
Kind of. It suggests the network learned some deeper structure about what makes a good tour, just from the examples. They did use beam search during inference, by the way, to help guide the network towards valid tours.
That's really significant, though. It means these networks aren't just mimicking. They're actually learning problem-solving strategies.
That's the major takeaway. Pointer networks show that neural nets can learn approximate solutions for these really hard combinatorial optimization problems purely from data examples. You don't need to explicitly program the complex algorithms.
So thinking about you, our listener, who wants that efficient understanding, this is potentially like a shortcut, right? Instead of mastering complex algorithms, maybe you could train a network with examples.
That's the potential, yes. Provide examples of the problem and good solutions, and the network learns to approximate the process. It's a different way to tackle these kinds of optimization or selection tasks.
Does the paper suggest other applications?
Definitely. They mention obvious things like sorting, where you're just reordering the input, but also broadly, exploring more combinatorial optimization problems seems like a promising direction.
Okay, let's bring it back to the core concept then, the big idea.
The key innovation is repurposing that attention mechanism, using it not just for context, but as a direct pointer, implemented via a softmax probability distribution over the input elements.
So it calculates probabilities for which input item to point to next.
Exactly, and that elegantly solves the problem of variable output dictionaries. The possible outputs are just the inputs themselves.
So, summarizing the whole deep dive, pointer networks are a novel neural architecture
Yeah.
that lets AI tackle problems where the output is selecting or ordering items directly from the input.
Right, using attention as a pointer.
And this overcomes limitations of older models and shows promise for learning solutions to complex geometric and combinatorial problems, like TSP, just from examples.
You've nailed it. It opens up new possibilities for learning these variable output tasks.
Definitely an aha moment there. The fact that a neural net can learn approximate solutions to NP hard problems just by seeing examples, that's pretty mind-bending.
It really is.
It makes you wonder, doesn't it? If AI can learn approximate TSP solutions this way, what other really complex planning or selection tasks could this approach unlock in the future?
That's the million-dollar question. It really expands the scope of what we might be able to tackle with machine learning.
For anyone wanting the deep technical details, definitely check out the original Pointer Networks paper by Vinyals, Fortunato, and Jaitley.
Yeah, it's worth a read if you want the nitty-gritty. But the core idea, that pointer mechanism, is powerful.
Absolutely. It feels like another step towards more flexible and capable AI.
For sure. It's exciting to think where architectures like this might lead.
Well, that wraps up our deep dive for today. Thanks for joining us on this exploration.
Hope you found it useful.
Until next time, keep learning.